First speaker is going to be Diego Munoz. Wait, I'm completely off. Diego Munoz. And he will tell us about the movie measurement.
Yeah, so my name is Diego Munoz. I'm here to talk about main characteristics of the Arepo code. Code that was written in its original form independently by Phurbas and has major contributors and developers both at the Heidelberg Institute for Theoretical Studies and the Institute for Theoretical Computation at Harvard. When I was thinking how to describe the code in one phrase, I came up with this. So essentially, since now we understand finite volume codes, Arepo uses a pretty conventional linear reconstruction muscle hydrodynamic finite volume scheme. But the spatial discretization is done in a less conventional way. It's a Born isolation of a set of moving points. And that means that each cell is a polyhedron that can be considered to be a quasi-Lagrangian volume that moves with the local velocity of the flow. While locally, so that gives it its Lagrangian component. Locally, it's solved by in the frame of the moving cells, reconstructing linearly all the primitive quantities, solving the problem, and calculating the thermal fluxes across the frequencies. Basic characteristics, well, that's the finite volume scheme. So we solve for the average quantities over the cell, or just the volume integrated quantities evaluated and assigned to the center of the cell. That's because it's a linear reconstruction. The gradients are obtained as a linear combination of the neighboring values. So it uses the Munoz theorem. We use the iterative Munoz solver, and that's because right next to the cost of the computation of the mesh, just using an iterative Munoz solver, the cost dwarfs in comparison to the mesh itself. The physics included are self-gravity, viscosity, MHD. Very simple radiated cooling was very complicated. It's really transfer for reionization, so we're missing something between to make a better approximation for cooling. Same accretion, black hole physics, galaxy information, models, prescriptions, etc. So just basically to describe the hydro part of the scheme, we use Born isolation of a finite set of points. The mathematics of the Born isolation are very useful because the solution is unique to a given set of points. In addition, the mesh varies continuously as the points move, as opposed to the Born isolation, in which you can have entire volumes disappear if you let the points move. Said in a more technical way, for between time step 0 and time step 1, you can essentially identify which cell is associated to each cell in the different time step. There will be topological equivalents. So using the neighbors, we find the gradient reconstruction. We reconstruct, we extrapolate to each phase. At the phase, the values move. We roll for half a time step. So after we solve the problem, we get the time center fluxes, and that's how we update the conserved quantities. So that's just a simple case of how the mesh looks in 3 dimensions. So there's really a small cosmological halo at the center, and the rest of the volume, the vacuum, is filled by a Cartesian grid. Now, just starting with the limitations. Well, the first thing I hear about this is that it's just too complicated and too expensive, and that is true. If you have no self-gravity, the most costly routine in the code is the mesh generation. For pure hydro, that can be up to 60 or even 70% of the CPU time spent in the code. However, if you compare to SVH, for example, the cost is comparable to the neighbor search routines and the smoothing over the kernel. So it is also, it needs regularization. If you let the mesh points move freely, the mesh will become tangled. So you need to massage the mesh to go from that to that. So that involves knowing where your measuring point is and how far you are from the center of mass of the cell. So you can pull, bias the motion of the measuring point toward the center. That is intrinsically a diffusing process. You're rearranging mass. Okay, so that's unavoidable, and you need to find the balance between the regularization of the mesh and how a tangled mesh can break your regularization, your scheme entirely. For example, an extreme situation would be forcing the code not to regularize in the case of a planetary wake in orbiting a star. If you don't regularize, this eventually will crash, but you can see how the measuring points will try to describe horseshoe orbits and essentially behave entirely Lagrangian. This won't work, so you need to regularize the mesh for this to work. So from this, you can already see that mesh regularization will be necessary when the flow is unresolved. You don't really need to do anything far from the planet, but in the horseshoe region, the orbital region, you have to regularize the mesh. Anyway, it's second order Hyperton space. That is not an intrinsic limitation. As we heard in the morning, there's PPM or higher order generalizations of PPM. Finite muscle Hyperton methods tend to be use linear reconstruction because it's much simpler. The case for that is that when you have linear reconstruction, both the average and the reconstructed quantity evaluated at the center are the same quantity. If you have higher order reconstruction, you either have to keep track of two quantities, the average or the value evaluated at the center, or to have a zero mean polynomial. You can choose whatever you want. The zero mean polynomial probably comes with fitting routines and optimization routines, so it will make it more expensive. The point is here that although we have linear reconstruction, it is a limitation, but there's space for improvement there. The self-gravity assumes point particles, and this is something that we're not too concerned about, but certainly something that deserves closer attention to actual measurements. When you compare to SPH, the SPH kernel is spherically symmetric, so it's reasonable to assume that in the monopole decomposition of the potential, you can assume that it's a point particle. In Arepo, we have inner cell structure, density gradients, and non-spherical shape. So clearly, the potential from that cell is non-monopolar. This could have consequences for the conservation of angular momentum, for example. And a thing, unfortunately, I'm not going to be able to talk much about because I'm not an MHB person, is the problem with constrained transport. So far, the MHB module works with the classic divergence cleaning or the Powell scheme. However, doing constrained transport in a code that, well, first has a complicated mesh, but second, the phases can disappear within 1 time step is certainly a challenge. At this point, I don't know if it's even possible, but certainly a problem there. Yeah, the expert there is really a Patmore who couldn't come this week here. So now I'm going on to the advantages. Well, the most basic thing is the reduction of detection errors. In a sense, the moving mesh code and solving the equations in the frame of the phase is a cheat similar to the Fourier scheme. Let's get rid of the bulk motion. Let's solve the equation of motion in that regime. Okay, that gives you several advantages. One is you can use longer time steps. Oblique discontinuities and shocks are captured for a longer time, especially in instability or something like that, because the mesh, the phases themselves can follow the discontinuity better, so that will provide you less mixing than fixed grid codes. And the infamous Galadini invariance, all these things are just consequences of allowing this mesh to move and solving the equations of the older equations in the frame of the moving mesh. So the classic movie, this is Kelvin Hamilton's ability, low resolution with a moving mesh, and you see how it develops in this scheme. Now, two things that could essentially inherited from SPH are the range of applicability. Essentially, we're not constrained by the geometry of the problem, so we want to apply it to problems usually reigned by SPH because we're not constrained by certain symmetry that can make the problem simpler. The mesh adaptability is Lagrangian, that is, we don't need, as opposed to AMR, the mesh, the code naturally concentrates cells wherever the flow is converging. Again, that's something that is inherited from the Lagrangian formulation. Simple example, I mean, the classic example is structure formation, galaxy formation. A simple example is just simply the weight of a planet in a disk. You can see that, where the weight is, we have a higher concentration of cells, where the planet is as well. And when we have a rarefaction, where the planets are soaking in a gap, we have a lesser density, smaller density of cells. And this is something that maybe little relevance for the hybrid community is something cute. We can put moving boundaries easily. The solid boundaries themselves can be part of the mesh, so they're tessellated as a part of the mesh. This is a classic example from the original Arepo paper, a lower resolution version. So we see here that we can add a solid boundary, which is the orange body there, by just setting a set of points such that when we tessellate the points, the interfaces between the 2 points are act as a solid boundary. The trick is to make this blue and red set of points, the solid side and the fluid side, move as a solid structure. On top of that, we can impose reflecting boundary conditions or non-fluid boundary conditions where the 2 cells meet. So the mesh or region partition, except for this spoon region, evolves in time until eventually relaxes and it looks just like a collection of polygons. So we can do it, I showed the mesh before. We can do it with a fluid that has 2 densities and see how the fluid mix by the action of the spoon. So this is called the copy problem, and we can just steer the fluid just by the action of the solid object until eventually it's all mixed. So in this case, we have reflective boundary conditions at the spoon and at the boundaries as well. Anyway, in the advantages with respect to SPH, well, I would say the basic ones most people would agree on. In particular, we're interested in the better treatment instabilities that are stressed, at least in one flavor of SPH, which is the standard version of gadget. Also, how, as Julius talked earlier before lunch, how SPH can treat turbulent cascades, or in the case of driven turbulence. So for example, I have this that we already talked about. What happens in the standard flavor of SPH when we convert a moving mesh code with a gadget code, with gadget for the same resolution, and see how the Kelvin-Hamilton instability evolves in time, and how the mixing is completely not treated well by this version of SPH. The other thing is the turbulent cascade simulations that probably we'll talk in further detail throughout the workshop, and it's something really interesting to know exactly why some of the flavors of SPH are not allowed to trickle the kinetic energy to trickle down to the smallest scales. I think that's it. Questions?
How often do you have to, I understand it depends on the process of the flow, but how often do you have to regularize the mesh? You don't do this every time?
So the regularize the mesh, you do it in principle every time, but it's not an aggressive process in the sense that it's proportional to how distorted the cell is at a given time. So if the flow is well resolved and the mesh, the cell in particular cell is not distorted at all, you will just, I mean, in terms of the cost, the loop is still there, but you will not add additional diffusion unless you really need it. Does that answer your question?
So I'm just curious, what is a good measure of the entanglement of the mesh?
So that's an arbitrary component of the code, unfortunately. We have at this point 2 measures. One is where the actual center of mass is, so consider the density gradient versus the measuring point. Those 2 locations are different in general. So if you don't want the mass to be too imbalanced, balanced within the cell, you kick the points toward the center of mass. The other criterion is, which seems to be more robust, is to use the angles subtended by the different phases. So if you have too much of a spread between angles, so a small angle and a large angle, you again will keep the measuring point toward the center of mass to avoid, essentially the extreme limit of that is ending up with hexagons in the case of 2D. So those are the two different criteria, and they're entirely arbitrary, unfortunately.
You kind of just determine the velocity, which determines the movement of one to the next point, and takes into the curve of that velocity field. Is that actually zero by any chance?
What is zero?
The velocity of the mesh transport velocity.
So yes, I mean if the velocity is, let's say, you keep the measuring point toward where you want to go with a given criterion, it is possible that that velocity will be zero. Just if the flow is, I don't know, one-dimensional or well-resolved.
But I mean, you want to have probably a tendency that this actually is at least as small as possible, perhaps.
Yeah,
Right.
yeah, it is as small as possible.
Yeah.
The criterion is somewhat complicated, but yeah, I mean, it is designed in a way that if you don't need to regularize, you won't regularize.
Yeah. Right.
The movie with the spoon looked great, but it seemed to me that there was some artificial structure built to the spoon.
Well, I mean, probably. It's a low-resolution movie. If you tell me,
No, not this one, but the next one.
yeah.
But I guess, again, I'm just asking, is this a question of resolution? Sometimes close to the spoon, something looks a bit
Oh, that's
squishy.
the rendering. Well, yeah, I mean, that spoon is you know, a few cells, and like 50 cells. But yeah, it's I mean, that's where all the action essentially is happening. It has no explicit viscosity, but there's some equivalent to a boundary layer there, and it's just completely unresolved. So yeah, I agree with that. Yeah, I thought you meant origin at the beginning. You essentially pulse it with the start of the spoon, and you trigger some waves that are essentially
okay.
survive.
But even later on, you see a little bit of stuff going on that looks a bit weird, I think. But
I mean, well, the boundaries are reflective, so you get. I mean, this is not a tracer. This is actual density. So you the bouncing back and forth should last for a while.
it's probably a question of adding more resolution.
Yeah, you can add more. Absolutely, can add more resolution. I mean, this is just a cube test more than a scientific test.
So,
More
can I ask-
questions?
one more question. When you were talking about the wake up generated by the planet,
Yeah.
was the planet a real Earth sphere or something?
In that case, it's just a rotating potential. In that particular example,
Okay,
it's
but
it's good potential, but
in principle, you could put a Earth sphere.
absolutely, yeah. I mean, like in this case, like with that, sure, yeah, that's something that we haven't thought of, but in principle, that is a possibility, yeah, for sure.
All right, let's thank the speaker once more, and then we move on. And now it's Colin McNally telling us about the Phurbas code.
Well, there's your first question, is how do you want to pronounce it? PH or PUR kind of sound. Phurbas or Phurbas? It's actually the name comes from Tibetan language. So transliterating into English is kind of a mess.
Why did you choose that name?
The name, okay, so this is what everybody always asks me. So, right, so Phurba in Tibet is a ritualistic dagger used in Tibetan Buddhism to chase off demons, slay demons. It also has the other kind of interesting quantity of it, two ones, is that it has a head of a demon itself, kind of on the top of it, and if it's used by a insufficiently skilled monk, since it's kind of has its own personality of its own, it will turn around and attack the insufficiently skilled user. This other thing that's kind of interesting is because they come from a culture without a whole lot of metal smithing. There's a number of examples of meteoritic iron. So.
There's also a Swedish cartoon about Phoenician for
Oh.
there.
Didn't know. There is also a movie called The Shadow with Alec Baldwin where there's a girl who goes around and screams at people. Anyway, right. So if you want to know more about this stuff, I should point out that there are two papers which actually go through all this and more. That are So, the first thing I noticed is when we did the program for this meeting, we got the term mesh-free up there. Just to point out, meshless and mesh-free, as far as I can tell, are the exact same term. They're used interchangeably across the literature. And what the idea, the properties of something that's mesh-free, what we're talking about when we say that, is that there are no edges that define a neighbor relation between your discretization points. So that is what makes this stuff different from, say, Arepo. Because Arepo, you have this set of neighbors you can follow to your first closest and second closest neighbors by following these edges between them. In a meshless method, you don't have that. So when you don't have those edges, you don't partition the volume into cells in some particular way. So there's no control volumes being invoked here. And one of the sort of curious things is that SPH is referred to as a meshless method. Although you can, well, it does have a sort of a neighbor relation in it, in the pairwise interactions between particles. So you can, in a meshless method, partition the mass into finite masses. And so that's how SPH, that's where SPH and Phurbas start different, is in that partitioning the mass and finite masses, that choice. So, where's the problem with SPH? Why would we actually go off and try and do something wildly different that may or may not work too well? Right, so SPH, although we refer to it as adaptive, I claim that it's non-adaptive, in that a fixed grid code is just the same as SPH, in that you pick how much volume you have per cell and you let the mass change. SPH is, well, you pick how much mass you have per particle and let the volume of the particles change. AMR, you have an arbitrary relation between volume and mass of each of your discretization elements. So there is another sense of adaptivity you can get. The other thing is what's referred to in at least a lot of the SPH work done by engineers, but this seems to have been first a problem before it became really notable to us in astrophysics, is the issue of zeros and first order inconsistency of the SPH interpolation. And what this comes down to, this is stuff that Julius was talking about earlier, what it comes down to is the relation between the particle masses and the densities. There is a relation they need to satisfy. I think this is pretty much what Julius was talking about when he was saying the very regular distribution of particles is necessary in SPH. There's only certain particle arrangements which really satisfy this zeroth order consistency relation. If the particle positions, the x's here, don't exactly satisfy this, that will be a not equals to 1, and you'll have finite amplitude wiggles in all your representation of functions, which feeds into things like the representation of pressure. But it can also, if it feeds into density, that can cause you issues with things like the growth of thermal instability from density perturbations. So yeah, this is the density computation SPH is this local weighted average on a kernel, and so that has shot noise basically in it. And that, so there are approaches, modified SPHs, which patch some of these things when they're doing gradients, but don't fix this up. So that means that when you're doing the conversion between conserved and primitive variables in the code, you end up feeding perturbations into the flow. And this is all related, this is again the same thing as the fact that in SPH the particle velocity and the fluid velocity are identified as the same thing. And that is what if you're trying to be strictly Lagrangian, that makes sense, because that's kind of what you mean by Lagrangian. The particles follow the characteristics in the flow. But in SPH, you need to make sure that the particles continue to sample the volume as they move around. So if you have two particles like this in a shear flow going past each other, they need to repel from each other a little bit so they don't come too close. And that means that they start moving sideways instead of just shearing. So you get these cross-stream perturbations, which then bounce around through the fluid until they get damped by their artificial viscosity. So this is an essential thing to making SPH work, but it actually, you see there, this is where we're going to, one way of understanding where the issue is gonna start showing up when you start trying to do very subsonic problems with SVH. So, what can we do about that? Couple of options. We can try and reduce the noise and the gradients. And so that brings us, I think, the large neighbor number SVHs, or high order SVHs. I want to use a larger order kernel, which has one tail that goes up further. There's been a couple of demonstrations in the last couple of years to demonstrate that that really works, works a bit. You can also do more complicated gradient estimates without actually changing that density estimate based on local weighted average. But this is the thing, there's no stubborn issue there is that weighted average, replacing it somehow. Because that's what you need to in SVH for converting between conserved and primitive variables. One way you can get around that people have come up with recently that works, is this thing about using Voronoi cells. So if you do the Voronoi cells and then run with them a little bit further, you get a Arepo. If you just do the Voronoi cells and then still use an SVH type of gradient estimate, you can get the Voronoi particle SVH. Which was mentioned also in a talk earlier today. Another choice there is say, screw it, let's just work in primitive variables and discretize directly on density and see where we can get. And so we start getting a method that resembles more in its philosophy a lot more like the pencil or stagger. Right. So that's what we're going to do. We're going to write a generalized sort of finite difference scheme on a moving set of points instead of a fixed grid. And that's really all that purpose is. So, how do we want to go about doing this? Right. One of the issues there, as soon as we start moving the points around, we're going to have an issue of what really is the resolution at each point of the flow. In that if we had a grid, the resolution would be set by grid spacing, right? It's just delta x. If you let those things move, then all of a sudden the evolution of the flow in the past is going to determine what your resolution is going to be. If you want to have an adaptive code, you want to be able to say what the resolution will be at any given time. So what you need to do is separate the resolution from the distribution of discretization elements. The reason you can do that a little bit is if you have too many resolution elements, too many discretization elements in a location, that doesn't necessarily mean that you have to resolve everything down to the smallest spacing between the discretization elements. So really, for any given resolution criteria, there is a minimum amount of local density of discretization elements you're going to need. But you can also have more, and that allowing that to happen is a useful thing to do in this sort of method. One of the consequences here of separating this apart is that when I do go to have moving points and I have to do neighbor searches, I don't have to iterate on the neighbor search to get a certain number of neighbors because the thing about my stencil size is going to be fixed by my resolution criteria, not my local distribution of points. What are we actually trying to solve in Phurbas? Well, this is what this is the Amici equations and Lagrangian derivatives over here. I'm going to stick in a finite set of points, not cells, not particles, just points in space. And so each of those points is going to have values of the primitive quantities on them. Density, velocity, internal energy density, pressure derived from the other things, and the magnetic field at that point. How do we actually go about this? At each point that needs to evolve in time, we define this scale lambda. This is our resolution scale. And in a sphere around it of 2.3 times lambda, we need to ensure that there is a sufficient density of points that there are no gaps here that are significant. So I can say what's happening to the motion around this point. Once you've satisfied that criteria, you can go ahead and do a moving least squares approximation, which is constrained to go through the point that I want to evolve, shown here in blue. So I take its neighbor values, and I do a least squares regression to find a third order polynomial that approximates that. And then that gives me my spatial derivatives. So what's happened here is that it's because in that least squares procedure, it doesn't matter if we have too many points compared to the number of polynomial terms that we want to fit, because it's the least squares thing, we're just going to minimize the error. So what we've done is we've freed up the resolution here from the particle distribution. So particles can get a bit further apart, and I can keep the resolution scale of my method about the same. Although at some point, if they get too far apart, I'm going to have to add a particle in. I can do this because I'm working in primitive quantities here. I just need to get an estimate of the density at this point, for example, and just add a resolution point there at the end of the step. Say a converging flow, I might have to do the opposite. I can just delete points, and I can still do the evolution of the neighboring points the same as I was before because of that. So what this comes down to is if this sphere is has a radius of 2.3 lambda, what this means is that there should be about one particle per lambda cube volume. So that's where this quantity lambda comes from. And that's going to turn into a minimum of about 50 particles per stencil that you're working with, which is one of these spheres. And then usually something more than that, because the particles are going to be always moving past each other. So you do need to have a couple more particles than the strictly minimal. So that there will be enough stuff there at the end of the step to move around. So now to come up with something that's stable, what we need to do is put some sort of dissipation in at the fine scales. And this has this took a little bit of experimentation, and this is just the thing that we found that sort of works. We've added two viscosity terms here, and momentum equation, and then the matching thing in the energy equation. These are bulk viscosities, these zetas. There are two components to it. Awful if you don't tune the knobs one way in Zeus, you get something nodding like this, with a linear and a quadratic viscosity, or a linear viscosity and a shock viscosity for L and S. Now, the thing is that I don't have a grid scale, delta X per se, to tie these two. What I have is this continuously changing in space and time resolution parameter lambda. So what I do is I introduce some auxiliary field. These things, the coefficients of these viscosities are actually evolved by a set of auxiliary equations, which consist of a fusion term to keep them smooth in space, a source term, and a decay term. So this linear bulk viscosity acts everywhere, and this acts to add extra dissipation and shocks. And I'll describe these more on the next slide. Right, so smoothing term, source term, decay term. So linear bulk viscosity has a source term that drives it up to a function of the signal speed and the resolution scale, just like you would in other linear bulk viscosities and finite difference methods. The shock viscosity works a lot like von Neumann artificial viscosity, although we've generalized it a little bit with extra triggers so that this can also occur in, it can also depend on things like magnetic field quantities around magnetized shocks, not just the divergence of velocity itself. Another trick here, which is similar to the time varying the artificial viscosity in SPH, is that you can make this thing rise quickly and then hang on and drop off after in an exponential manner by having different time scales in the source and decay term here for the shocks. So it go rise up fast and then drops off, just like the Monahan 987 artificial viscosity in SPH. And then also, this is also similar to SPH well, sorry. No, this isn't similar to SPH. Well, sorry, there are some versions of SPH which do something like this. Say that one. Around shocks, you also want some extra diffusion in the continuity equation and energy equation to keep those quantities smooth around shock. It seems. But this is kind of artfully designed. Other details of what's going on here. The div B, we seem to, there's a couple of approaches you can use. You can't use CT because you don't have control volumes. You just have points in flow. So you could use a vector potential. What we have chosen to do, we have found works just fine in what we've done so far, is use the magnetic field directly in the discretization, and then just add a single term that is awfully like a Denner cleaning scheme, where you just diffuse away div B. This form, the Lagrangian form here of the induction equation, this is something pointed out in a couple of MIT SPH related works, is that this form of the induction equation advects magnetic monopoles as a passive tracer around when you break it out this way. So they don't really cause much immediate instability when you left to damp away when they do occur. They're very small, it seems. So the order details here, these are third order polynomials, so that's, you can think of it a lot like third order finite differences in space. We use a second order Hermite vector time integration scheme. And because of all these procedures are specified per particle, we have easily adopted individual time steps for each particle. That's not much of a generalization to do that in this context. We have also stuck in tracers here. Basically, tracers are just a set of points which never get added or deleted and evolve the same set of interpolations and time integrations as the rest of the gas. We wrote this code by building on the back end provided by Gadget 2, because all the tree operations some of the tree operations are quite similar. The thing about adding and deleting points constantly is unfortunately quite different than exists in Gadget already. So, but how it works. Convergence test, alpha waves. We get our second order convergence coming out. The point here is that the bulk viscosity does not affect shear motions. This convergence rate, this alpha wave, which is the shear motion, shows that. That's unlike, unfortunately, in SPH, where your bulk viscosity, because the particles do have a head-to-head closing velocity, even if they're going past each other, your bulk viscosity in SPH ends up causing a little bit of shear viscosity at the same time. And to show you the adaptivity, how that actually works out pretty nicely. This is a solid chalk tube with a spatially constant refinement. This is one with mass refinement. You can see here that in the lower density shock there, the shock is getting wider because I'm decreasing the resolution in this case versus this case. But other than the change in resolution, the flow was reasonably unaffected. Shock tubes, there's far more discussion of this in the paper, so I think I'll leave it for there. And you can do MRI, you test that out, you get some convergence coming out. The number of lambda per wavelength that you seem to need isn't too different from what Mario found for fixed grid codes. So this lambda and delta x on second or third order grid code seems to act reasonably the same. We run some things like disks. So here's a cylindrical disk model that goes circling. Just to show you that does sort of work. And what's going on here is that this is a large periodic volume with only high resolution in this center area, and then the resolution drops quickly outside. So there's no hard boundary here. That's how you can use, say, the resolution in a fixed manner. Yeah, that's the point distribution from that. So you can do things like, even though the density is varying smoothly across here, to vary the resolution, the density of discretization points very steeply, to find a big buffer if you want to, like in AMR. And one of the tricks then you can do that once you have kind of Lagrangian additivity is you can do things like put in moving high resolution regions. We already developed flow to see how that behaves. And to point that out actually here, see here is that unlike AMR, the resolution can vary continuously in space. I'm not sure if this is actually a huge advantage. It is theoretically interesting that this can happen. That you don't have these factor of 2 jumps in resolution anyway. So there's, for example, the current density and the same thing at the same time with this high resolution patch added. And you can develop much finer structures in the current sheets there. And you can do things like analyze current sheets on a small scale. Test. Caveats of doing this, because we discuss strictly at primitive quantities and not on finite volumes or finite masses, there is no local conservation. Once you do that, you can't really, unfortunately, you don't have the infrastructure you need to define local conservation, so you can't really get it. The speed of this is slower than grid codes. This is a lot of the same issues as Arepo and SPH will. With the added problem, well, one of the benefits is you don't have an iterative neighbor search, but you get the not having an iterative neighbor search by adding and deleting points from your tree. So depending on how you arrange things, you can get some overhead there. So really, the fact is these Lagrangian codes only make sense when you need the flexibility of this kind of discretization. There is a lot of overhead, as other talks mentioned earlier. And this is just a thing with, also shows up in SPH, a lot of SPH work with individual time steps is one of your limiting factors for scaling often becomes the fact that you can have a small subset of points or cells or whatever with the smallest time step, and then you're spending most of your time updating that small subset. So that problem hasn't gone away. Also with this sort of very open style of this meshless arbitrary style of discretization, doing things like implicit time inversion, which is something that I'm beginning to think is more and more useful, is very difficult in this sort of a setup. So yeah, here's your summary of stuff Phurbas has. And so these are where you can go read about it. And this paper is a subject of the first talk tomorrow, too, where we do more competency stuff. And we'll talk more about subsonic flows at that point. Questions?
Please.
Yeah, so I do have a
Yeah.
question. So your code is based on tangent, so you use a tree to define the, but I wonder if you use a particle in cell, would that be more efficient?
Well, it depends on the point distribution. So, well, yes, if you have a very even point distribution, particle in cell is more efficient than a tree. It's when you have clustered point distributions that the tree was, right? For a lot of the stuff we're doing, it's well, let me show you, for example, where I bet you in here, particle and cell is good. In this, I've got about a factor of 100 in particle point density between here and far out of the box, where there's that buffer region. So I'm still thinking a tree is probably the best thing there. Although that's a common problem a lot of all these adaptive codes have.
What are the known side effects of having some divergence of B in the simulation. Are you aware of any?
The big one that people talk about is that the code crashes.
Anyway, that's not so important because then it crashes.
Yeah, so this is one of the things that does give me a little bit of concern, of course, when you acceptable div B. I don't really have a good general way other than to say it's not a problem, other than doing a careful convergence study.
Does anybody else have any idea? Yeah.
There's a paper by Garrett Toth where he compares all these different methods,
Oh, with
Including-
the strong
including,
shocks.
including the 8-wave method, for example.
Yeah. Is there a
Well,
simple
not
way
strong.
to talk about what he saw a bunch of anomalies, but is there a way to talk about what is a div B anomaly, other than measuring it in the discretization at one time? Like the side effects of
get
div.
Lorentz force, right?
Yeah, you get Lorentz force parallel to the field.
Right.
Yeah,
And
So-
I mean, the result that Toth reported is wrong jump conditions for
yeah,
some of the Roux-Jones test models.
yeah.
Because there's a anomalous force at the interface. And because even if div B is small, because the shock is very thin, it's a very large force. It doesn't converge away.
Yeah, so that's one thing is well, if you're gonna have a method that does that, you need some way to vary how big the div B errors are of that shock. So things like increasing the resolution while keeping the shock at a constant width would help that. So basically increasing resolution, but also increasing the artificial viscosity in the shocks.
Well, it's certainly true that making div B smaller helps.
Yeah,
You know,
so that's what I'm saying is the only
add
generic way I know
fusion
of
if you
to
want.
actually look at that is do a really careful resolution study. So that's one thing where this is why I point out that you can do, and there is actually, we have in here up to first order in time, the A formulation. Because you just don't technically have to worry about the different.
And that actually works, or does it not work?
That works. The reason not is that you are probably giving up a little bit of accuracy, because in effect you have to take an extra spatial derivative of A.
And that I don't think is a problem, but the problem I think, and Alex might have told you that, that you accumulate large divergence, large gradients in the A field. If you have a Galilean invariant conversion of that.
I haven't run into that.
We have a paper on that, which talks about that. 2011. It's of course.
All of that.
How do you do the individual time stepping?
Block time steps in the same way that Gadget organizes them, around to a factor of 2. One of the things is because the update of each point is what happens is your slow time, the course time step particles get interpolated using the predictor part of the predictor corrector. Which is the predictor part is second order itself. We're actually doing the first and second time derivatives, which unfortunately comes with some ugly long expressions. But that lets us project forward in time those course time step particles up to the current fine time level. Then you just gather up, do your least squares, and recalculate the new time step for this fine particle. Because there's no pairwise exchanges between the particles, they don't have to know that they're being used in another particle's time step when they're just drifting forward in time.
Okay, maybe one last question, and then we move everything else into the coffee break.
Coffee break, yeah.
Sorry, made this a point of discussion.
Yep.
That's kind of related to AR codes. It's not immediately obvious that the density field is the best thing to be refining on, and that you should always move to nest points where the density is going. Perhaps it's more important to follow the magnetic field, because there may be more structure in that, especially where there's no mass.
That's one of the
Maybe it's the
reasons.
temperature that really is very important to model this. I mean, of course, you have the ability here to, generically change the points, but you still have to explore all these options and decide which variable. After all, rho is only one component of the of the vector of unknowns, and why should it be the most important component that we should always adapt to that? So, are you planning to sort of investigate more generally?
I think that's awfully problem dependent.
I'm sure it is.
I'm
sure it
and
is.
that's a huge
Certainly,
field of
yes.
research, I think, in
As far as turbulence goes, there's one way to use vorticity as a trigger that has been explored with flash, I believe, in ISM turbulence.
well, that actually brings us to an issue which I'll address more in my next talk, which is quantifying uncertainty. Because really, I guess what you want to do is you want to put resolution in a place that decreases the uncertainty in your result. So then you need to wonder, where is the uncertainty coming from?
But how flexible are you with this method to decide where you can put your resolution?
It can't change too quickly in time or space.
No, in terms of variable that you choose, that you start.
Arbitrary. It is literally any function of x, y, z in time. So, you know, I've forced this moving resolution patch in here. This is a specified function that's moving. That's not tracing the flow actually. That's moving structured AMR, if you will.
And just follow up on Jim's, and if I understand what you are saying, you actually have a hybrid approach. If you have a disk, then say you choose the density field in the mid-plane, but say the magnetic field.
Yeah, that function lambda is an arbitrary combination of inputs. So, yeah, it could
So the key point would be, if I understand correctly, is to choose the function form of lambda with some of the variables in some region of space,
Yeah.
which minimizes
minimizes the uncertainty on whatever physics answer you're looking for.
Mhm.
That's a significant art, I think. Yeah.
All right, let's thank the speaker once again and all. And then I would say we do half an hour coffee break and reconvene for the brainstorming session. And CK has one announcement.
Yes, so for the conference dinner, if you haven't paid, then you better do it during the coffee break, because we will pay for the ordinary. So for all the registered participants, you pay $300, we will pay half. But if you want to bring in extra person, then that person will pay the full price, that's $600. So, yeah.